I welcome you all to the third lecture in the series. Today, I am going to introduce you about the work and heat transfer in engineering thermodynamics applications. Prior to this, in first and second chapter, already you have been introduced to different kind of systems where you have got an exposure of basically three types of systems: closed system, open system, and isolated system. Closed system is the one which is having fixed mass, alright, and energy may cross the system boundaries, while open system is the system in which both mass and energy cross the boundaries of the system, while the isolated system is the one which does not interact with its surroundings either by work transfer or heat transfer, right? So any closed system can interact with its surroundings either via work transfer or heat transfer. These may be called energy interaction, and these bring about changes in the properties of the system. So thermodynamics basically deals with the study of these interactions and the associated property changes of the system. So when we talk about work transfer, right? So work transfer is one of the mode of energy transfer. In mechanics, in your 10 plus 2 study, you would have studied the general definition of work transfer. In mechanics, the action of a force on a moving object is identified as a work. So here, force is the means of transmitting the effect from one object to the another object. But the force itself never creates any physical changes except when it is coupled with a motion. So force is not a form of energy. So as per the mechanics, work is said to be done by a force when it acts on a moving body in the direction of force. So the action of a force by a distance is termed as work transfer in mechanics. But when we talk about the thermodynamics definition of work, here it is slightly different. So work transfer as per thermodynamics is said to be done, a system is said to be done a work if the sole effect on the things external to the system can be reduced to raising a weight. So weight may actually not be raised, but the net effect would be of raising a weight. Let me explain the thermodynamic definition of work by a simple example. Let's consider a battery and motor combination as my system, right? So system is having its boundary, right? So boundary usually may be real or imaginary, as I already stated in the first chapter. So this is the system boundary. So system consists battery with motor. So battery basically operating this motor, and motor is coupled with a fan. So fan is not a part of our system. Basically we are considering battery and motor as our system of consideration. In this case, how actually work is getting transferred as per the thermodynamics? Let's see. So Soul effect external to the system. So this is the system. What is external to it? External to it is the fan. So if I replace this fan by a pulley and a weight, then battery will operate a motor, and motor can drive the pulley, and pulley can raise the weight. If that scenario happens, as per the thermodynamic point of view, there will be a work transfer involved by the system basically. So here system is doing the work on the surroundings. So basically in this way also work is getting transferred, because Soul effect external to the system can be reduced, so it can be rearranged in order to make a weight to be lifted. Is that clear? So as per the thermodynamics, both the cases work is getting transferred, because Soul effect external system can be rearranged to raise a weight. So thermodynamic definition is slightly different. So again I am repeating, as per the thermodynamics, work is said to be done if the Soul effect on the things external to the system can be reduced to raise a weight. This is known as work transfer as per the thermodynamic point of view. Now, as I said that work unit is basically Newton meter, right? So work is basically Newton meter, or we can say joule, alright. Now, work done per unit time is known as power, right? When you are calculating work per unit time, that will become the power. Now let's go for the sign convention, how actually when we will consider work to be positive, when we can consider work to be negative. Consider this as a system. This is my system. Everything external to it is surroundings, and system is bounded by boundary, right? So this is my boundary. So sign convention I am discussing here. Sign conventions. So two sort of things can be positive, either work will go inside or work will go outside. If there is a work input to the system, that means external source is doing work on the system. That kind of work transfer will be considered negative. So work input will be considered negative. Whereas if system is doing work on the surrounding, that will be considered as positive. Keep in mind, when there is a work on the system, that will be considered negative. When system is doing work on the surrounding, that will be considered as positive. So these are the sign conventions, right, to be followed, right, regarding the work transfer. So as I said earlier, work is not a property of system basically. So anything which is not a property of system will be called as path function. So basically this work transfer depends on the path or process. So work transfer will be different for different kind of processes involved. So as it is not a property of system, so it does not depend on the points or state points, it depends on the path. So it forms inexact differential, basically inexact differential. So we cannot integrate that. We cannot integrate that. So let us consider the case of the work transfer, right? That is, we used to say PDB work as well, right? Displacement work. So let us consider a piston cylinder device. This is my piston cylinder device. Here is the piston, and it is filled by a gas, and gas is my system of consideration. So it is filled with some gas. So it is system, so I am drawing the system boundary. So this is my system boundary, right? So this gas is my system, right? This is my system boundary, right? So let's suppose the initial condition here is P1, total volume P1, temperature T1. Now let's suppose some changes are happening, due to which there is an increment of pressure, and as pressure has increased, it will push the piston backward, and piston has moved to a new position. So this is my first position. If I say this is first position, now piston has gone by a very infinitesimal distance. So now this is the second position. So if I say this is second position, and it has moved with a very small infinitesimal length dl due to the pressure exerted by the system, right? Over here, let's suppose the now system as it has gone like this, and this is basically the rod. So now system boundary has gone up to here, all right? Final condition system boundary is up to here. So this handle is not the part of our system, right? But this space is the part of our system. The final condition is going up to point 2. Initial condition is here. So when it is going to here condition becomes P2, V2 and T2. Right. Let assume, right, a gas is my system. Initial condition P1, pressure P1, total volume V1, absolute temperature T1. Now, as there is some infinitesimal change in pressure, due to which piston moves by an infinitesimal distance dl to the right side. So final pressure becomes P2, volume V2 and temperature T2. So and system has done the work against surrounding. So surrounding is here. The system has done work against the surrounding. So let's suppose small a is the area of the piston. So small a is the area of the piston. All right. And let's suppose this has moved. So my volume got changed by very infinitesimal small quantity, right? Very infinitesimal small quantity. So the pressure force exerted on the piston will be pressure into area, right? Pressure into area. This much force is getting exerted on the piston due to increment in pressure of gas, right? So the work transfer, so if I say infinitesimal work transfer, so I am writing this, or you can write dou w, because I said work is not an exact differential, so I cannot write dw. So I can write dou w or cut dw. It's nothing but force into distance, right? Distance is dl. So dl is the distance. So force is, this is the force, right? So P into A into dl. So area into length, this will give us the infinitesimal change in volume dV, right? Area into dl will give the infinitesimal change in volume, so P dV. So PdV is my displacement work. Boundary is displacing, so displacement work. So let's suppose between the point 1 and 2, if I want to write W1 to 2 or 1 W2 is equal to integration between V1 to V2 PdV. So this is my displacement work, right? This is applicable for non-flow processes where flow basically is not happening because system is having fixed mass of gas is not going to change. So this formula is applicable for non-flow processes or closed system where mass is not going to change but volume is changing. So it's a PdV work, or we say this as boundary work, or we can say displacement work, right? Boundary work or displacement work. So integration of PdV is only possible if my process is quasi-static. That means each state passed through by the system will be an equilibrium state. If process happening at a very fast rate, I cannot get the integration of PdV and I cannot find out basically the boundary work if the process is happening at very fast rate, right? So if my process is happening very slowly, or if I say my process is quasi-static, then only I can get the displacement work or boundary work. So if I want to represent this over the thermodynamic coordinates, right? This process on thermodynamic coordinates, how will I represent? I will draw here. So if I draw, this is volume ordinate, this is pressure ordinate. So this is going from one state to another state, from 1 to 2. Alright. In between there are number of equilibrium states, right? So let's consider one point at midway somewhere over a period of travel of piston where pressure is P and change in volume is dV, right? So area under this curve basically will give us work transfer. So area under the curve on PV plot, this is P1, this is P2, this is V1 and this is V2. So area under the curve over the PV ordinate will give us the work transfer, right? So every state passed through is a quasi-static equilibrium state and this process is quasi-static process, right? So P into dV, if I integrate between 2 points V1 and V2, I can get the displacement work or boundary work. The integration is only possible when the process is quasi-static. Note this point somewhere. If process non-quasi-static, we cannot integrate this. That means we will not be able to find out the displacement work if my process is not quasi-static. Is that clear? So displacement work is given by this, and keep in mind I cannot write W2 minus W1 because it's not an exact differential, so I am writing W12 or 1 W2. It's a PdV work. Next topic. So is that clear? So next topic is cyclic process, right? Cyclic process. I said that cycle was defined. Cycle is defined that if it is a series of processes, right, in which the end of one process is the beginning of another process. At the end of the cycle, the initial and final states will be the same, or we can say that there will be no net change in the properties of system, right, after the cycle. So cycle is something like this, right, starting from some point and reaching here. So it's starting from 1 and going 2 and return back here. So In a cyclic process, there is no net change in any property of system. So I can say cyclic integration of total volume is 0. Cyclic integration of dP is 0. Cyclic integration of dt is also 0. So there is no net change in any property of system, or there is no net change in energy of the system in a cyclic process. If process is cyclic, total energy remains constant, right? That is not going to vary. So note this point as well. Next topic is PDV work for various kind of processes, right? PDV work for various processes. How to find it out? So let's we start from very simple process that is called isobaric process, or sometimes we say isopistic, pistic process. So it is a process in which pressure remains constant, right, while system is changing its state from point 1 to point 2. So here pressure is constant, and such process is known as isobaric process. So if I want to represent this over the PV diagram, it will be very simple. So this is volume and this is pressure. So it's starting from one point going out to another point while pressure is constant. So pressure is constant, but my volume is changing basically. So volume got changed from V1 to V2, and this area under the curve basically will give us work transfers. Here pressure is constant going from 1 to 2, right? So this is the process representation for constant pressure. So if I want to write the work transfer W1 to 2, I can say integration between V1 and V2 P dV, and assume that is a quasi-static process, so I can integrate, I can get P into V2 minus V1. So this is the work transfer in a constant pressure process. Easily you can get. Second is isochoric process, or we can say constant volume process. So volume is constant. How will I draw that? I will be drawing in this way. This is pressure, this is volume. So volume is constant, so it will be simply like this. Any process up and down, right? I'm assuming it is expansion. So this is the process, right? So this is my P1, this is P2, and volume same B1, B2 is equal to V1 is equal to V2. So if I want to find out 1 to 2, V1 to V2 PDV, that will be 0. So displacement work for constant volume process is 0, right? These are the two processes that we have seen. Let's go for the third process. Third one is isothermal process. Isothermal process, that means temperature is constant. So temperature will be constant only when my P into V is equal to constant. If this term become constant, right, from ideal gas equation of state, if PV is equal to constant, I can get temperature is equal to constant. So as per this, I can say P1 B1 is equal to P2 V2 is equal to P into V, that is constant, right? This is equation number 1, right? So if you look at this equation, this is nothing but x into y is equal to c. So it is equation of hyperbola, right, basically. So if I represent over PV, coordinate, this is P, so I can draw one hyperbola kind of thing. So 1 to 2, right? So this process is PV is equal to constant, so I can connect V1 and V2. So this area basically I need to find out, right? This is called as work transfer. So this is P2, this is P1. So this is the process basically we need to find it out. So this is the work transfer at the end of the curve. So how to find out that? W1 to 2 is integration of V1 to V2 P into dV. So from this, look at this. So from here, from equation number 1, I can write P is equal to constant, or consider this P1 V1 divided by V. If I substitute here, this is from equation number 1, I am taking P is equal to P1 V1 divided by V and substituting here at place of P, I can write P1 V1 is constant, V1 V2 dB by V. So if I integrate this, I will get log, right? So log, usually we say base power 10, so ln, so I can say W122 is nothing but P1 V1 ln of V and V1 V2. If I apply, you can get P1 V1 ln of V2 divided by V1. This is W122. Now what is V2 by V1? So V2 by V1 will be P1 by P2. From this relation I can say V2 divided by V1 is equal to P1 by P2. So I can say this again, P1 V1 ln of P1 divided by P2. So this is the expression for the work transfer in isothermal process. Clear? Like that you can write. And furthermore, if you want to go, you can say this is mRT1 ln of P1 by P2 by using the equation of state, or if you are writing the specific volume, then just RT1, right? Ln of P1 by P2. Alright. So this is work transfer in isothermal. Let's go for next one. Fourth expression. So fourth one, work in polytropic process. So polytropic process is a process which obeys the law called PV to the power n is equal to constant. Right? Any process which follows this law is known as polytropic process. So characteristic will be something like this, slightly cubic, right? Some power will be there, cubic, and we can represent here. So we can write now equation in this way. So using this I can say P1 V1 to the power n is equal to P2 V to the power n is equal to PV to the power n is equal to constant. This is my equation number 1. Clear? So from here I can say P is equal to constant and V to the power n. Now work, that is V1 V2 PdV, substitute the value of P here. So V1 V2 constant dV by V to the power n. Constant is constant, take it out, integrate this, B minus n plus 1 divided by minus n plus 1. Alright, V1 V2, so you can write constant, this is V2 1 minus n, V1 1 minus n, right, divided by 1 minus n. You can write in this way, right? Now substitute the value of constant. So constant may be either P2 V2 power n or P1 V1 power n. So corresponding equations you can multiply with the constant. So 1 divided by 1 minus n, right? So when you are multiplying with this, you can write P2 V2 into V to the power 1 minus n. When you are multiplying with B1, that constant, you can say P1 V1 into V1 power 1 minus n, right? Clear? So like that you can write. Wait a minute. Okay guys, so let's start again. So this is basically n, here also n, right? So now you solve this. So look at this, one n is here, another n is there, cancel out. So you will get very simple expression here, that will be So work transfer is nothing but P1 P2 V2 minus P1 V1 divided by 1 minus n, or you can say P1 B1 minus P2 V2 divided by n minus 1. So this is the work transfer, right, for polytropic process, right? You can write in this way, or you can write in some other way. And second method is also there. This is the one way in which you can represent. Second way, take P1 V1 as common. If I take P1 V1 common and n minus 1 is also common, take this out. This can be written as P2 divided by P1 into V2 divided by V1. So just look at this. So from this equation number 1, I can say V2 divided by V1. So V2 divided by V1 can be written as P1 by P2 to the power 1 divided by n, right? From this expression I can say V2 divided by V1 is equal to P1 by P to the power 1 by n. If we substitute here P1 V1 divided by n minus 1 minus, this is P2 by P1 into P2 by V1 is this, right? So when you are substituting this, if I want to write this P2 by P1, I can say this as P2 by P1 to the power minus 1 by n. So if I substitute this here, P2 by P1 to the power of minus 1 by n. So this will become P1 V1 n minus 1 bracket 1 minus P2 by P1 to the power 1 minus 1 by n. So solve this, you can get W122 is equal to P1 B1 divided by n minus 1 minus P2 by P1 to the power n minus 1 by n. So this is another form of work transfer in polytropic process. Either you can use this or you can use this. Now look at here, we are getting P1 V1 and P2 V2 because we assume like process like going from 1 to 2. This is basically expansion process. In that pressure will decrease. If it is a compression process, reverse compression process, then this term will be P2 V2 minus P1 V1 divided by n minus 1. So don't make any mistake, right? For expansion process 1 to 2, it will be P1 V1 minus P2 V2 divided by n minus 1. If you are going in reverse, that is called compression, it will be P2 V2 minus P1 V1 divided by n minus 1. So it is very simple. So we have derived expression for polytropic. We have derived almost for every type of processes. Now go for a combined PDB diagram. How does it look like? So if I draw here volume, this is pressure, this is a point 1, right? This is the point 1. So if it is going like point 2 here, and again I am representing some other point where processes are going like this, then this become vertically down. So let's suppose this is n is equal to 0, this is n is equal to 1, this is n is equal to 2, this is n is equal to 3, right? This is n is equal to infinity, right? So like that we can represent. So any value of n starting from 1 and 1.2, 1.3 or whatever, those all are polytropic processes, and based on that value polytropic process may convert into some other kind of process. So if I write P to the power n is equal to constant, this is general polytropic process. If I put n is equal to 1.4, the moment it will become P to the power 1.4 is equal to constant. So 1.4 for air, this is gamma, so this will become P to the power gamma is equal to constant, which is nothing but reversible adiabatic process. Reversible adiabatic process, clear? Or adiabatic process. So it is P power gamma is equal to constant. So work transfer, right? In this case also formula will be almost similar like polytropic process. So this I will give you as a homework, you try with. So for reversible adiabatic process, you can derive expression for work transfer that will be similar like this expression you will be getting in place of n, just you will get gamma. Alright. So this is one thing. Similarly, if my n is becoming 0, that means what? P is equal to constant. This is a constant pressure process which is represented here. This is a constant pressure process when n is equal to 0. if I n is becoming infinity, if my n is becoming infinity, that means what? What I am trying to say? If my n is becoming infinity, that will become volume is equal to constant, right? This is known as isothermal process. When my n is infinity, right, this will become constant volume process. And for any other value of n apart from 0 and infinity, that is known as polytropic process. When my n becomes 1.4, this will become adiabatic process. Keep in mind, first condition n is equal to 0, it is not a constant pressure process, right? N is equal to infinity, it is known as isocoric process. When n is equal to 1.4, it is adiabatic. And one more condition, when n is equal to 1, it will become Pv is equal to constant, which is known as isothermal process. Isothermal process. So for different value of n, you will have different kind of processes. N is equal to 0, constant pressure. N is equal to 1, isothermal. N is equal to 1.4, it is adiabatic. Any other value apart from this will be polytropic. When n becomes infinity, right, I got isocoric or constant volume process. So like that, any kind of process can be derived from the polytropic process. That's why we say polytropic process as a general thermodynamic process. Is that clear? Okay, so now let's go for these are all, these all formulations are applicable only for quasi-static process. Process is not quasi-static, you cannot integrate PdV work, or you cannot find out the PdV work. Let's go for next discussion. Apart from this, other modes of work transfer, other modes of work transfer, other modes of work transfer. Apart from the PdV work, there are several other work involved in the nature. That is called electrical work, shaft work, right? Or you can say pedal wheel work, magnetic work, surface tension work, right? Even though those are all works, right, if you add together, that is called total work input or total work transfer in a system. So I will summarize some of the other modes of work transfer. There are also work transfer apart from this quasi-static process work transfer. So first is called electrical work. How does it happen? So let's consider electrical current carrying resistor, right? This is a resistance, is carrying I current, and this is the boundary. So let us consider a resistor carrying the current as my system. So there is a work transfer into the system basically, because we are supplying work from some external source. So there is a work transfer into the system, and I said if you are supplying the work to a system, it will be called negative work. So in this case it is a negative work, so I can say current is dc by dt, right? dc is a charge, per unit of time is called current. So you can find out the work. So work will be E into I, right? Simply potential into I is my work transfer. So in this case work transfer will be negative. This is the first kind of work, electrical work. Second is called shaft work. So shaft work means a motor is there, motor is coupled with a shaft, and shaft is rotating at some t with some angular deformation d theta, right? It's rotating. I am considering shaft only as my system, right? This is my system, shaft is my system. So if I am considering shaft as a system, that means shaft is rotating, there is a work input to the system by a motor, the shaft is rotating, right? So how to find out the work in this case? W1 to 2 in this case will be T into d theta between 1 and 2 basically. So if I am saying it's rotating between two states 1 and 2, and by a torque and angular deformation theta, so work transfer involved, right, on the shaft, that is means negative work, motor is doing work on the shaft, that is known as T into d theta, angular deformation. So power power will be dw by dt. So that is nothing but t into d theta by dt. So this is the torque into omega, angular velocity. So this will be the power transmitted, torque into omega in the case of shaft work. Consider the third case, paddle wheel or steering STIRRING, steering work, right? How will it happen? Let's suppose one closed system is there and is fully insulated. It is insulated and it is fitted with a fan, and fan is connected to a pulley, and pulley is connected with a weight. So weight goes down, pulley rotate with T. There's a work transfer involved into the system, right? This is fully insulated, right? This is a pulley. So such kind of system is there. This is called paddle wheel and paddle. So why as the weight goes down, it rotates the rod, right, shaft, which rotates the fan. So there is a work transfer into the system, right? In this case, even though volume is not changing, if you look at container volume is same, so PdV work is zero basically in this case. So displacement work is zero in this case, but there is a work input due to what? Due to which means due to the shaft rotation, and that will be equal to the loss of potential energy of weight. So if I say the work transfer dW will be mg dz, let's suppose it's going by dz height, is equal to t into d theta. So if I want to find out, I have to integrate between 1 and 2. So this is the work transfer in the case of paddle wheel or steering work. This is also negative work. Basically you are doing work on the system. So in all these forms we are doing work on the system. So this is paddle wheel or steering work. Next one is flow work. So flow work means flow work is applicable to the system in which there is a flow. That means there is a mass and energy transfer crossing the boundaries, and such systems are known as open systems. So open system, let's suppose I am assuming one open system here, something like this. So this is my open system. So this is 2, this is 1, where pressure is P1, B1, T1, right? Here P2, V2 and T2. So this is my system boundary. So this is my boundary. Here some gases will come with mass 1, right, and will leave with mass 2, right, and nothing will accumulate here, right? So the work input here, right, when the entry is dW is nothing but P into dV, total volume. Let's suppose infinitesimal amount of mass is entering, that infinitesimal amount is dm. Dm is an infinitesimally small mass of flow which is entering. So this total volume can be written as P into dm into specific volume. A specific volume into mass is known as total volume. So dm is the infinitesimal amount of mass flow rate, B is the specific volume. So work input can be written as P into dm into V, right? So at entry we can say flow work W dW entry can be written as P1 V1 dm1. Similarly dW flow, right, at outlet is P2 V2 dm2. So this is entry, this is outlet flow work, right? I can get P1 V1 dm1, P2 V2 dm2. Or in general flow work is given by dW flow, that is nothing but P into specific volume into dm. This is known as flow work. So apart from these, right, apart from these works, there are magnetic work, surface tension work, right, and so many other work, right, chemical reaction effect works. So there are various kind of work. So total work, right, total work is nothing but summation of all, summation of displacement work, displacement work plus stirrer work plus electrical work plus dot dot dot. So if you add everything, that is called total work transfer in a system. Total work transfer in a system. Like that you can calculate the work transfer. Is that clear? So these are these other works, other mode of work transfer apart from the quasi-static work transfer. So let's go for the last topic for today. Last topic is basically free expansion, free expansion, free expansion with zero work transfer. So we need to discuss whether free expansion is possible without any work transfer. So assume the first case. This is a container in which gas is filled here. This is a gas which is filled here. This is my gas and this is vacuum basically. So I am assuming gas and vacuum as my system. In between there is a partition. This is partition. Partition is there. This is my first case. So if I assume gas and vacuum, right, this side is vacuum, this side is gas, and this is separated by a partition is my system. If I remove this partition and let gas to rush and fill the entire volume of this container, right, even though the gas volume got changed, if you look at gas volume got changed, but whether there is any displacement work involved or PdV work, no, because system boundaries are fixed, that is not going to change. So as system boundary is not going to change, as we know that work transfer is a boundary phenomena, that means it is a form of energy in transit crossing the boundary. So at boundary nothing is happening, right? So whatever volume is changing, that is changing only for gas, as it has made allowed to expand, right, and finally occupied the complete volume. So even though volume of gas got changed, but there is no net change of the volume of the system, so there is no PdV work involved. Clear or not? So the expansion of gas against vacuum is known as free expansion. So vacuum does not offer any resistance to the flow. Well, there is no resistance offered against the flow, that means there is no work expenditure done by the flow. So there is no work transfer involved in this case, right? So expansion of gas against the vacuum does not require any work transfer. So there will be no work transfer. This is the first case, right? So here PdV work is basically PdV is 0, right? First case. Now consider the second case. Second case, if I consider only gas as my system, gas is my system, this is partition, right? Here is a vacuum, so vacuum is not my part of system now. So if I remove now partition, what will happen? Now only system is this, right? So the moment I remove the partition, my system volume got changed. So my system volume got changed. So one definitely will think about calculating the PdV work, but problem is that process is not quasi-static. The moment you remove the partition, gas will rush and fill the entire volume. So process will happen at very fast rate, right? So it cannot reverse. So process is not reversible. It's not quasi-static. So PdV work is not involved. So in this case also, PdV work cannot be calculated. This is cannot be calculated, right? in first case here in this case, as this was the system, right, here work transfer was 0 because there was no change in volume. So there is no change in volume, work transfer was 0, but PdV for gas, if you want to calculate, that is not equal to 0. If you want to calculate PdV for gas alone, even though this complete system, for gas alone PdV can be calculated, that is not equal to 0, but overall work transfer is 0 because work is defined only at the boundaries of the system, and the boundary nothing is crossing, so that's why net work is 0 because dV is 0, right? But PdV for gas can be calculated, but it does not carry any meaning, right? But in this case, the moment you remove the partition, gas will rush at a very fast rate and fill the entire, volume. So even though my boundary got displaced, right? Now something is crossing the boundary. But problem is that we cannot calculate that because process is very fast. It's not quasi-static. So if I want to represent our PdV ordinate, P into V ordinate, right, this will be simply represented by 2 points 1 and 2, and I cannot connect by continuous line, so it will be dotted line. Dotted line means it is an irreversible process, or you can say non-quasi-static process. So integration of PdV is not possible for non-quasi-static process, so I cannot integrate this. Here again work transfer is not involved. Let's suppose third condition, if you assume now, this is my gas, this is my system only, this is system boundary, and this vacuum place I am putting n number of partitions, right? These are n number of partitions, small partitions, these are all partitions. I will remove partitions one by one so that the expansion is very slow, right? Process is very slow. So I am making this very quasi-static process. So if I represent over this, I will get now continuous line, right? I will get now continuous line between 1 and 2, and in between I got n number of equilibrium state. Now process become quasi-static. So one by one I am removing. But problem is that this area vacuum is there, and vacuum basically does not offer any resistance to the flow. As there is no resistance to the flow, there is no work transfer, there is no work involved either to the system or from the system. So work again is 0, but process became quasi-static, but work transfer is 0. So we can say all of, as a summary, free expansion is a 0 work process, right? So free expansion means expansion of gas against a vacuum is known as free expansion. If that is happening in any case, either fast or slow, it will not involve any kind of work transfer. Clear? But you got an idea in which case you will have quasi-static process, in which case you have non-quasi-static process. If process is fast like this, it is a non-quasi-static process. If it's a non-quasi-static process, I cannot integrate this PdV for this kind of process. So non-quasi-static process will be represented by only single point, 2 points and states, and it will be connected by dotted line, and it is not having any meaning. So it's not connectivity between point 1 and 2. Only quasi-static processes can be represented over the PV diagram by a continuous line. So third case is the quasi-static process, because we are making our process to happen very slowly. So it's a quasi-static process. Even though it's a quasi-static process, we are not going to get any PdV work because there is no resistance basically offered by the vacuum. So pre-expansion is termed as the 0 work transfer process. So today I am closing my discussion here. So today we have covered the work transfer. We have seen the derivations, how to solve and find out the work transfer in quasi-static processes, right? Different kind of processes. Apart from those quasi-static processes, you have seen different kind of other types of work transfer involved, mechanical work transfer involves, that can also be calculated. And finally we have concluded with the free expansion, and free expansion has been proved that it is a 0 work transfer process. With that, I am closing today. In next topic, we will be covering the heat transfer, and we will see some practical application, practical numerical problems based on these concepts. So thank you for listening today. Have a nice day. Good day.